Hi. I come straight to the point where the most new acoustic engineers struggle for the first time. You just make the recording an NVH measurement and now you want to analyze it using an FFT spectrum. But there you have to set the right block size. So what is the right block size? Well, that depends on the sampling rate you're choosing for the recording, but even worse, on the signal you have recorded. What's in there, what you want to see in that signal. So actually, it's very easy to make a big error on that point. And therefore, in this tutorial, I will show you the effect of different block sizes on different signals and show you that is the best setting here for, and there you should better use that kind of setting, okay? And working since 20 years as an acoustic engineer, I give you my personal recommendation. When I have a measurement, what is the setup I use first that always fits? Well, first of all, you have to understand, why do we do an analysis? Why don't we just listen to the file we just recorded? Well, we want to have a picture. If I want to talk about a picture like this one, it's extremely easy. See that picture? It's a beautiful landscape. I love this river from the right to the left. And in the end, this big, massive bridge. It's confidence. And here, a hidden place, a beautiful garden around. I love to be there. Here on top, you see a blue sky with a small white cloud. I love that. And all is surrounded by these green trees. But maybe it would be nice to have someone sitting in here with a fishing or maybe a small boat. That would be perfect. It's extremely easy to talk about a picture because you can point on different areas, see what's in there, and describe it with words, okay? So you can work on that picture. There's something I should add, and you will understand. It's so easy. Now you do this in acoustics. You hear something, playback. There's this noise. It's like I can't imitate that. Can you play back? Okay. You know what I mean? No. Yeah. You can't point. You can't hear it specific what you're talking about. You just hear the big noise at all. Okay. And that's why we want to have analysis that makes the audio recording to be a picture. Okay. And the typical setup would be a frequency tracker. The best way to illustrate the effects is I'm using a synthetic signal. It's modulated signals. It has 48 kilohertz sampling rate, okay? And the analysis, the common one would be an FFT spectra. That will be over time. Just default setup, and I want to see that in the marker analyzer. What I see here, I see some frequency lines at low frequency, 100 Hertz, something about 800 Hertz, and here on top also clear sinus constant signal. Let's listen to the file if this is what I hear. No, definitely no. It has high frequency, fast changing effects. There's a softly drops down that I might see in here, but also below there's this boom, boom, at 100 Hertz. If you're only looking at small devices, you can't hear the 100 Hertz. If you have a proper device, you hear the full spectra, okay? So this is the wrong setting. Obviously, when I listen to the file, I see that setting is wrong. First tip, listen and compare with the signal that you see if it's good. But so we have to work on that. Obviously, my time resolution is too small to catch this up. You need to understand the principle. A Fourier transformation always choose a number of samples and then looks inside the signal which frequency are inside. And then from here to there, the next samples get it and also frequency I get it. You can mix it a little bit, but in the end it's just stepwise making frequency analysis step by step through the full signal. The longer your block size is, the longer your analysis time, you can also look at lower frequency because the full cycle is in. So for low frequency, you need a long block size. But of course, if the signal is changing during the while, you miss that because it's just average to nothing, all right? So what you need is sometimes a really small block size to follow step by step what is the signal right now, but then only high frequency content will be detected. So this is the crucial point in the FFT setup. Let's check this in the analysis here in the software. I go for the analysis again and have a spectrum size of 4096. I love this option here. You can have a preview what setting you will reach with this setup. At 48 kilohertz, we have 11 hertz. So we only 10 times in a second we can change the value. This is too less. If the signal has changed already during the run, you just get that one. You get just anything averaged, okay, and you lose the information. So shorter block, and it can follow these easily, all right? So make this happen. I go here maybe for 256, really short block size, and recalc by pressing that button here. And that's what I want to see, okay? Now we had this on high frequency, but as you can see here, your time signal get lost. You have only 187 Hertz frequency resolution. In comparison, that gets clear. Before, we can clearly see we have a tone at 700 Hertz. But now there's only a big cloud, something between 900 and 600, because you only can divide 200 Hertz segments. Any frequency in between is just added to one value. That's the crucial point. You want to have a higher time resolution. You can get it, but you're losing your frequency resolution at the same time, okay? So if you have a frequency resolution of about 200 Hertz, you can't see anything below 200 Hertz. So this signal, okay, this is extreme. Let's go for something realistic, a real measurement. Here I have a door closing. Recalc again with the standard setup of 4096. Okay, I see one big bang and then it gets softer. Let's see if this is right. No. There's more. There's a See, I will slow down the speed, then you can follow me easier. Unique proper devices, okay? So there's definitely more than what I see in here. But we learned a lot, okay? All we need to have higher time resolution. So again, we go back to 256 and recalc. And there we got what we want to see. And now we play back slowly. Okay, but again, like before, we miss the low frequency content, which is not that right, because if you're just looking at the time signal of this recording, you see this frequency content is low, it's wobbled around in the room. This is the dominant energy in that recording, and you miss it because you have to also concentrate on this high frequency content in the totally beginning. So what to do? One way would be you always have to do different setups. You start with a long block sizes to get the frequency, then you go for lower block sizes to get time effects, and then you have to mix it anyway. Yeah, there's a better way. Give you my trick. Switch time signal off. Let me put the mark analyzer below, so we have access to the mark analyzer and my project at once. We add another analysis. I want to have a spectrum. I want to see the frequencies. But there is more than just the FFT. I go for hearing model versus time, just default setting, and just drag drop this on that point here. And there it is. You see the information, we have two impacts, and and the low frequency also drops at 50 Hertz. So if I want to compare these two analyses, I just put this here on, what do we say, 256, and this and that should be added, so it's controlled to this mark analyzer. I can see better now. I have the time resolution are needed here in both cases, no? But if I play back, this effect is a little bit clearer in here. But most of important is here only frequency up 200 Hertz will be shown up, and here we go down to 50 Hertz. So in this special low frequency content noise, hearing model has a directly advantage. We have the time resolution and the low frequency content in just one shot. Okay, that's I like this. Yeah, keep that. I will keep that there, right? But this is an extreme example. We have a really short time information and also low 100 Hertz frequency content. If you have other kind of noises, something that stays in the frequency, like woo, yeah, this disadvantage is not that big. Let's check that. I have a ghost in here. Just drag drop it and analyze both analyses at the same time. Here, see, this is some weird rattled noise. This seems to be wrong, but my FFT spectrum is definitely here fine enough to follow the line and give me the clear tone information we have. Wow. And this is, let's listen. Okay, this is still slow motion, but it's let's play back faster. That's the richtig speed. Yeah. Again, I just have to make this a little bit faster. 256 is not enough. Damn. Okay, this bird has it very fast changing altitude. So maybe I should go to 64 to catch that one. Yeah, now it looks similar again. Okay, so this effect quite often happens. Okay, but if I have a really constant noise, just a fan running, woo, no changing altitude at all, okay? Got some example for that as well. I have here 4 constant fan noises and calculate an FFT spectrum. According to the FFT spectra, fan number 1 looks the best. Fan number 2 has some tones in here. Fan number 3 looks quite fine for me, and fan 4, well, at low frequency we have some contents here, 200, no, we clear tone in there, okay? That's the message I just get from the FFT spectra. Let's looking at the hearing model spectrum. Same scale, but here this still looks the best. Here again some frequency, but a little bit of unconstant. But this is strange. We have a clear, fat, strongly fast alternating tone in here. We didn't see that in the other ones, didn't we? Let me see, this is all the FFT spectra again. No, this is completely fine. Well, so who's right? Listen to the file. He's fine. Second. There's this 200 hertz. And the third one. Very annoying tone. And the fourth one, that's a loud and wide frequency noise. I got only wide single tones there, like the FFT analysis shows me here. The FFT analysis always provides the same frequency resolution over the full frequency spectrum. Always. Humans have different frequency resolution depending on the frequency. Always. That's why there is no FFT setting that matches human perception. That is the problem. Let's concentrate on 3. I can see here it's such a clear line, and here it's just a rough line. Why this is a completely different interpretation. This is a really important effect. If I just open my cursor line and see this is the main tone in there as a reference, and see the next tone as 75 hertz apart of it. And that's something, if you have 70 hertz between 2 tones, the human ear cannot divide. It's in the same bark. We hear that as an alternating tone. So we hear the first tone alternating in its amplitude, which is not. There are 2 tones, but I hear, okay? And this effect is so clear and takes my attention. So in the hearing model, this effect is also included. If there are 2 tones too close together at 70 hertz, it would show me as a rough tone, because that's what I hear. And that is the problem. Okay, how much should I reduce this part here? And you can see directly if the picture looks better, the sound is better, because this picture is now exactly displaying what you hear, and therefore it's like you're talking about a picture. So to summarize, what is the best setting for an FFT spectra? There isn't. You only can do errors. It's in the mathematics of the Fourier transformation. You always struggle to have high time resolution and high frequency resolution at once. But actually what you need, you want to have the time resolution of human hearing, that's the threshold, and the frequency resolution of human hearing, because that is the customer. And that is why this hearing model do exactly this kind of analysis. It picks the signal and calculate it like it's heard by a human with a cochlea, with all these magic effects in there. And then we have time and frequency resolution over the full spectrum like a human has. And so on one shot, you hear what you see. It's a little bit weird that people who want to calculate the frequency spectra always check first the FFT analysis. Keep in mind, the Fourier transformation has been developed in the year 1822. This is over 200 years now. Mr. Fourier comes with horses to the university to develop that, okay? So we have developed trains, cars, electricity, computers, okay? There have been a lot of new inventions. Why shouldn't we lose that, okay? If I'm going to a train station, I don't looking for a steam train because this was the official first train to do a spectrum analysis. No, I go for a new fast train, maybe a magnetic ride, okay? It's just one click away. So clearly recommend. The first analysis on any acoustic signal you have is the hearing model. You see the problems, you can discuss the problems with your problem. That is the reason why all our devices have two main outputs for headphones. Two people can listen to the file and talk and work on that file. If you can't listen to the file, you end up like maybe make a third octave spectrum, and maybe if you draw the line, it will be better. Maybe. If you have the time, yeah. But don't ask for good sound design. It's just dropping the level. I think the best thing for you now is if you try this algorithm on your own measurement data. But how can I get this algorithm on my computer? The so-called Sottek hearing model is one of many modern high-performance analysis that has been developed by Head Acoustics in the field of psychoacoustics for the NVH sector. This gives you the advantage that it's already fully integrated in the Artemis suite. Just click on it and you got the result. If you do not have this module or this program at all, you can apply for a free trial license. Then we can unlock it for you on your computer via the internet. And then you will notice in direct comparison to the FFT what advantage it will bring you to be suddenly 200 years ahead. Apply here and thank me later. No, this just can't be. There can't be an analysis to solve all the problems that easy. No. If you think that way, you probably need more background information on the analysis Sottek hearing model. At first, I feel the same way, of course. And that is why I personally asked the developer of this analysis, Professor Dr. Sottek, what's the background, what's the idea behind of this analysis? You can just watch the interview by clicking on the follow-up video up there. And then you can still apply and test it and make this huge step ahead towards good acoustic development.